Hello, students. Today's topic is alkenes, and alkynes. Before we start, please hit the subscribe button. And if you like the video, please. First is our alkenes. For alkenes, general formula is CnH2n plus 2. So, let us see some examples of alkenes. That is this. Okay. So, here you can see if we take n equal to 1. So, 2n plus 2 comes 4. Here if we take n equal to 2, then it comes 2 into 2 plus 2, that means 6. And for this, if we take it 3, then 6 plus 2 equal to 8. So it is our methane, it is our ethane, and it is our propane. So that's how we know that this is a alkene, just by calculating from this formula CnH2n plus 2. Okay. And also there is double or triple bonds here, so it's alkene. So let us see the preparation reaction for alkenes now. First is our decarboxylation reaction from carboxylic acid. Okay. So if we want to derive a alkane from a carboxylic acid, so we have to go through this reaction that is called decarboxylation reaction. So let us see what happens here. That is, we give NaOH or sodamide. So here we also can write it like this, NaOH plus CaO. Okay. So here it gives us RH. Okay. So that means it is a C minus 1 reaction. So what is C minus 1 reaction? That is, if we take example like this, and if we just do this process again, okay, what happens? This comes CH4. Okay. So here we had 2 carbons. Okay, here we had 2 carbons, but here as you can see we have 1 carbon. So that's why it's a C minus 1 reaction. Okay, so the number of carbons we have taken for carboxylic acid, it will be the alkane will be uh, minus 1 carbon in the product. Okay, so if they give you an acid and tell you what will be the product of the decarboxylation reaction, so then you just do minus 1 and then just make it a alkane. Just like if we do this. Okay, so then what will be the alkane here? If we do the same decarboxylation reaction, just count the numbers of the carbons, 1 2 3 4. So it gives us propane because it is a minus 1 reaction. The second is our Savatian-Sanderen process. It is from alkene. Okay. So as you can see, if we want to derive a alkane from its respective alkene, so we have to do this Savatian-Sanderen process. For this, we take an nickel catalyst and heat it to 240 to 250 degrees Celsius. Now, this is based on the principle of adsorption of hydrogen or occlusion. That is, hydrogen get absorbed on the surface of this Ni metal, and now if we heat it the hydrogen goes out and breaks the double bond and gets attached with it. So that's how it gives us CH3 CH3. Okay. So when they give you this Ni 240 to 250 degrees Celsius, just you have to remove the double bond and put a single bond here and add the number of hydrogens needed for a alkane. That's how you do this. So it comes CH3, CH3. Next is our Grignard reagent. Now here, in case of Grignard reagent, it's a very important reaction because when you go later on, so we can see that this Grignard reagent is used in many cases. So let us see. For Grignard reagent, what we have to do? We have to react it with H2O. So here it acts like this. Okay. Now what happens? This 1H gets broken and gets added to this CH3. So what the product will be then? That will be our CH3H or CH4. Okay. So that's how we derive alkane from Grignard reagent. Next is our Clemenson reduction reaction. Okay. So if we want to derive alkane from its respective aldehyde and ketone, so then we do this Clemenson reduction reaction. So let us see what happens. That is, the reagent is Zn plus HCl. Okay. So we will just write what is given in the question without this double bond O. Okay, so we have written it RCH. It is also here RCH. Now in place of this double bond O, we will just add 2H. So what that gives us? That gives us RCH3. So for this question also, we will do the same. That is, without the double bond, we will write the entire molecule. That is this. And in place of the double bond, we will just add 2 hydrogens. So that will give us RCH2R dash. And here also, it will be like this. HH, but we don't write the H here, right? So we'll just write it like this. And for this also, just write the entire molecule without the double bond. So it will be like this and add this 2 hydrogens here. Okay. So next is our Ulf-Kishner reduction. So it is also will be same as our Clemenson reduction, but its reagent is different. That is, we take hydrazine NH2 CH3O minus K plus 180 degrees Celsius temperature. If we give it, then it is as same as the Clemenson reduction. That is, we write it without its double bond O and add 2 hydrogen in the place of it. So it gives us RCH3. Okay, but its reagent is different. Okay, and it also gives us alkane from the aldehyde and ketone. So just remember the name of the reaction, that is Ulf-Kishner reduction, and the reagent of it. Okay, because they ask you the name reactions. Next is general reduction. Now, here in case of general reduction, what happens? We give red phosphorus plus HI and heat it on 150 degrees Celsius. Then what happens? Gives us RH. Okay. So that means if we take CH3OH, it will give us CH4. Now RCHO, it will be like this. We just remove this double bond O, like the previously mentioned reduction, Ulf-Kishner reduction, and add 2 hydrogens here. It's easy, right? It will be RCH3. Next is, again, we're gonna write it without the double bond and add 2 hydrogens here. But what will happen when we have this RC double OH? That means it's a acid, so you don't have to worry about it. So you just count the number of bonds it is attached to. Without this R, because RC is the principal or base of the alkane. So 1 2 3, so 3 bonds without this R, so just add 3 hydrogens here. It is as simple as that. Okay, so it will give us RCH3, right? So number 7 is our Uth reaction. So if we want to derive the alkane from alkyl halide, we do this Uth reaction. Now here reactivity of 1 degree alkyl halide is greater than 2 degree alkyl halide, greater than 3 degree alkyl halide in this Uth reaction. Next is for the halogens. So as you can see, I2 will be more reactive than Br2 greater than Cl2. That means RCl is less than RBr less than Ri in reactivity of Uth reaction. Now this is a C plus 1 reaction. That means we have seen C minus 1, that the product gets one less carbon than the reactant. So here the product gets plus 1 carbon in the from the reactant. So what happens, that if we just add Na dry ether, it gives us RR. Okay, so what will be the trick to do it in the exam? That is, just separate this Cl and R, okay, and add another R with this R. That means let us take it for CH3, that is CH3Cl is given. So now in the exam they give you Na dry ether, so you know that this is Uth reaction. So what we have to do, you just separate this CH3 and Cl in 2 parts and add the another CH3 with this CH3. Okay, so that will give us C2H6. So that is our product. So that's how we do our Uth reaction. Now second question is kind of tricky. That is, we have taken 1 mole of this molecule here, so we can add another molecule like this CH3. So what we have to do, then if the Na dry ether will be given, so how will the Uth reaction will be formed here? That is, it gets bonded in between. Okay, so the Br bond gets open and the Cl bond gets open and it gets bonded in between. So the product will be like this. So but in the third question they given it as excess. So now the main question is where the reaction will take place, whether the Br bond will get open or the Cl bond gets open. So for that, what we have to do, that is, we have to see the reactivity order. So what is the reactivity order? That is Ri greater than Rbr greater than Rcl. So that means the Br bond here will be more reactive than the Cl, right? So the Br bond will be opened. So if we just give it Na dry ether, so it will give us a molecule like this, because Br bond gets open. Okay, so this will be the molecule, right? So next is our Kobler's electrolysis. There is a fundamental what we can say drawback in this Uth reaction. That is, if we take CH3Cl plus C2H5Cl here and give it Na dry ether, now what will be the product? Now it gives us 3 products. Okay, so what are the 3 products? That is, as I have told you, just break this Cl and CH3 and Cl and C2H5 into different parts and add one CH3 again here, that is CH3, and one C2H5 again here, that means C2H5 C2H5. But here in this case, but two different or asymmetric alkyl is given here. So what we do, that is, we add this CH3 with this C2H5. So that gives us 3 products here. So that is the fundamental adversity here. Electrolysis, what happens, that is, if we just write this molecule like this, okay, so what happens, it again the double bond O will gets opened, and also this ONA bond gets broken, and respective number of hydrogens will be added here. That means 1 2 and 3 hydrogen will be added here. So that will be our CH3 CH3. Okay, so that's how Kobler's electrolysis is formed. But there's a trick here. That is, if we uh, do Kobler's electrolysis of this molecule, so what happens in electrolysis? The bond gets broken, obviously, but what happens? The bond doesn't take hydrogens; it forms a double bond here. Okay, because so then what will be the molecule be looking like? That is, so we can just form the double bond in any of this because it is added to the 3-degree carbon, right? So we just add the double bond here. Okay, so the molecule will be looking like this, the product final product. So next is this. So again, what we have to do for, then we are just gonna break this bond. So then it will be added like this, right? Double bond. Next is our this molecule. So for this again, we have to break this and the bond will be added here. That is this. Okay. Next is this. We again have to break the bond. So double bond will be formed here. Next is this. Now here is a characteristic difference from the previous ones. That is the double bond is already present here. So the product, we are just going to write it like this. That is the triple bond will be formed. But as it is a triple bond, that is why it is sp hybridized. So that means the final product will be linear. So we will write it like this. Okay, so this will be the final product, not this, because of the sp hybridization, it gets linear shape. Now this. Now many of you are thinking that from the previous of this question, here the triple bond is getting formed. But as you can see here, that here triple bond can't be found because sp, if it gets sp hybridized, it can't be linear here. So what happens? The bonds gets broken and it will be added with another of same molecule. That means molecule will be looking like this. Okay, so this will be the final product. Next is our reduction using amalgam. So the reagent of this, that is ZnAgHCl. So it will be same as other reductions what we have done previously. That is, it gives our RH. Then we just take it without the double bond and add to hydrogen in place of it. Here also we do the same thing. Okay. So that will be the reduction, but the reagent here is ZnHgHCl. So the reagent is important. The next is our Scorehouse synthesis. Now that is, if we take one alkyl halide and two Li, that gives us RLi plus LiX. Now from that, in second step, 2 RLi plus CUI, it gives us R2 CuLi plus LiI. Now in third case, R2 CuLi, it gives us R dash I and RR dash plus RCu plus LiI. Now it gives us this alkane here, right? So that's how Corehouse synthesis is done.